Okay, so we've seen that propositional nets can be used to advantage in searching game trees. The other main use of Propnet nets is in analyzing games. For example, by analyzing the Propnet for a game, it's sometimes possible for a player to detect structure that allows it to actually decrease the size of the game tree in significant ways. Game decomposition, or so-called factoring, is a good example of this. A compound game is a single game consisting of two or more individual games glued together. The state of the compound game is a composition of the states of the individual games. On each step of a compound game, the players perform actions in each of the individual games. The compound game is over when either one or all of the individual games are over, depending on the type of the compound game. Now, using the techniques we have seen thus far, compound games can be quite expensive to play. Unless a player recognizes that there are independent subgames involved, it's likely to search a game tree that's far larger than it needs to be. For example, if one subgame has branching factor A and a second has branching factor B, then the branching factor of the joint game is A times B, one choice of each of the B actions for each of the A actions. And then the fringe of the game tree at depth D is likely to be something like A times B raised to the power D. Now, this is wasteful if the two games are truly independent. In that case, there are two trees, one with branching factor A and one with branching factor B, and the total size of the fringe of these trees at depth D should be only A to the D plus B to the D, significantly smaller. Double Tic Tac Toe is an example. On each move, players play on one of the two boards. The first to win on either board wins the overall game. If the game is left unfactored, the branching factors are quite large. There are 81 possibilities in that first move, 9 for each board. And then there are 64 in the second, and so forth. However, if the games are factored, the branching factors are much more modest. Game factoring is the process of discovering independent games inside of larger games. Once discovered, game players can use these factors to play the individual games independently of each other and thus cut down on the combinatoric costs of playing such games. It turns out that it's often easier to discover independent subgames using the Propnet representation for games rather than other representations. Now, in this segment, we'll look at some elementary techniques for factoring games using Propnets. We'll first talk about discovering factors with completely independent subgames. We then talk about factoring with interdependent termination and rewards. And after that, we talk about factoring with interdependent actions as well. And finally, we'll discuss briefly conditional factors, that is, factors that appear only in certain states of the games, but not in all states. Okay, so let's begin our discussion of factoring with a simple case of a compound game consisting of multiple completely independent subgames, only one of which is relevant to the overall game. Without factoring, the player is likely to consider actions of all of the subgames when only one of those subgames matters. Now, this is admittedly a very special case. It doesn't arise often, and it can be solved by means other than factoring, but not by the methods we've seen thus far. Nevertheless, it's worth considering because it prepares us for factoring more complicated sorts of games. Okay, multiple buttons and lights is an example of a game of this sort. The overall game consists of multiple copies of buttons and lights. In each copy of buttons and lights, there are 3 base propositions, the lights, and 3 actions, the buttons. Pushing the first button in each group toggles the first light in that group. Pushing the second button in each group interchanges the first and second lights in that group. And pushing the third button in each group interchanges the second and third lights in that group. Initially, all of the lights are off. The goal is to turn on all of the lights in the middle group. The setting of the others doesn't matter. Now, here's a Propnet for the game. Notice that there are 3 disjoint parts of the Propnet. One portion for the first group of buttons and lights, a second portion for the second group, and a third portion for the third group. And note that the goal and termination conditions for the overall game are based entirely on the lights in the second group. Looking at the Propnet for this game, it's easy to see that the game is this very special structure. The Propnet consists entirely of 3 completely disconnected subnets, one for each subgame. Finding factors in situations like this is really easy. It can be computed in time that's polynomial in the size of the Propnet. And having found these factors, the solution is really simple. The player just keeps the essential component and discards the other two. Now note that this technique can be applied equally well to multiple player games. For example, multiple Tic Tac Toe, that is 3 games of Tic Tac Toe glued together in which only the middle game matters. The Propnet for multiple Tic Tac Toe is similar to the Propnet for multiple buttons and lights, and it's possible to find the structure in multiple Tic Tac Toe just as easily as for multiple buttons and lights. Okay, now let's consider a slightly more complicated case, namely compound games with interdependent termination. We can assume interdependent goals as well, but I'm going to ignore goals for now and just focus on termination. As with the case of independent subgames, entirely independent subgames, actions are partitioned over distinct subgames and there are no incoming connections between those subgames. The main difference is that the termination condition for the overall game can depend on more than one and perhaps all of the subgames. Now, in games of this sort, the termination of the overall game can be defined as any Boolean combination of conditions in the individual games. In the case where the combination is a disjunction, the game is said to be disjunctive. In the case where the combination is a conjunct, the game is said to be conjunctive. As a simple example of a factorable game with disjunctive termination, consider best buttons and lights. In multiple buttons and lights, only one group of buttons and lights matters. In best buttons of lights, the compound game terminates whenever any group terminates, not just the one in the middle. This gives the player the freedom to play whichever subgame it likes and rest assured that if it succeeds on that subgame, it succeeds on the overall game with the same score. Okay, here's a Propnet for best buttons and lights. It's similar to the Propnet for multiple buttons and lights, except that the goals and termination are based disjunctively on all 3 subgames. The good news is that we can extend the technique just discussed. Let's consider the simple disjunctive case. If the connective leading to a termination is a disjunction, as it is in this case, with its inputs in turn supplied by nodes in different subgames, then we just simply cut off the overall termination condition and make the termination in each of the individual subnets a termination condition for that subnet. When we repeat this process, as long as we encounter only disjunctions. If the game is truly disjunctive, this will eventually lead to a separable Propnet like the one shown here. Now, if the process does succeed in factoring the Propnet in this way, then the player simply picks one of the subgames and proceeds as with the case of independent subgames. Alternatively, and better, the player tries playing all of the subgames and picks the one with the best score. Or at least that's the basic idea. Unfortunately, it's not quite that simple. There's a problem that does not arise in the case of completely independent subgames. The player may choose one subgame, find a winning strategy, and begin executing that strategy. Unfortunately, in the course of execution on the chosen subgame, one of the other subgames may terminate, terminating the game as a whole before the strategy in the chosen subgame is complete. This can lead to a lower score than the player might have otherwise expected. The solution to this problem is to check each of the subgames for termination when no actions are played in that subgame. The player takes the shortest time period and plays each of the other subgames with that as a step limit and takes the one that provides the best result within that step limit. For the subgame with the shortest termination, if there are no other subgames with that step limit, the player tries the next shortest step limit and so forth. Although in this approach the player searches all of the subgames more than once, this is usually a lot less expensive than searching the game tree with the unfactored game because it does not cross-multiply the branching factors of the independent games as it would if it did not use the game's factors. And once again, it's possible to extend this technique to multiplayer games, though this has to be done with some care. Okay, finally, let's look at compound games with interdependent actions. Interdependent actions. By interdependence of actions, we mean those actions have effects on more than one of the subgames of the compound game. Okay, now at first blush, it might seem that games of this sort are just plain not factorable. However, that's not necessarily true. Under certain circumstances, even with interdependent actions, it's possible to identify factors and use those factors to search the game tree more efficiently than without considering the factors. Okay, here's an example. This is called joint buttons and lights. As with the other buttons and lights variants that we've seen so far, the lights in this game are organized into groups of 3. However, unlike the previous variants, buttons are not associated with specific groups. Instead, each button has effects on all 3 groups. Button AAA toggles the first light in each group. Button AAB toggles the first light in the first group and the first light in the second group, and interchanges the values of the first and second light in the third group, and so forth. So we have all possible combinations of the actions in the preceding games. Although all of the buttons in this game affect all of the subgames, the game is still factorable with just 3 actions per factor. The reason is that there's one button in the compound game for each combination of actions in the other 2 subgames. Thus, the game trees for each subgame can be searched independently of each other, and the actions chosen can be reassembled into overall actions of the compound game. For example, if action A is chosen in the first and second subgames and action C is chosen in the third subgame, then action AAC can be performed in the compound game. Okay, now recognizing when this can be done is not easy, but it is doable. There are just basically 2 steps. In the first step, the player groups actions into equivalence classes of actions for each subgame. And in the second step, the player determines whether these equivalence classes satisfy what is called the lossless join condition. Finding equivalence classes is done by looking at the propnet for each subgame. 2 actions are equivalent if they are used in the same way in the propnet for that subgame. For example, if each action is input to an AND gate with the same other input, and if the outputs are connected by an OR gate, then the effects of one action cannot be distinguished from the effects of the other action, hence they are equivalent. The process of finding equivalence classes is repeated for each potential subgame. In general, the equivalence classes for each subgame will be different. In fact, as we'll see, in order for the game to be factorable, they must be different. Once a player has equivalence classes for each potential subgame, it then checks whether those equivalence classes are independent of each other. The criterion is simple. Each equivalence class in one potential subgame must have a non-empty intersection with each equivalence class of every other potential subgame. If this is true, then these partitions pass the so-called lossless join criterion. More details in the notes. If a player finds equivalence classes for various for potential subgames and they pass this lossless join test, then the player can factor the games into subgames. In order to benefit from the factoring, the player must modify each propnet so that the individual actions are replaced with the equivalence classes of which they are members. This cuts down on the number of possible actions to consider. Otherwise, the branching factor of the game trees for the subgames will be just as large as the branching factor for the overall game. Once this is done, the player can then search the game trees for the different subgames to select actions to perform in each subgame. It can then find an action in the compound game for the particular combination of subgame actions. This is always doable provided that the partitioning of actions satisfies that lossless join property. The player then performs any action in the intersection of the equivalence classes chosen in this process. Okay, again, check out notes for more details on factoring games with interdependent actions. Finally, let's look at one more case, namely conditional factoring. That is factoring in cases where a game is not factorable to start out, but over time becomes factorable. Here's an example. It's called linked Tic Tac Toe. 2 games of Tic Tac Toe connected by a single square that connects the 2 subgames. The goal of the game as a whole is for the player to get 2 lines, a row, column, or diagonal of that player's mark, with at least 2 of the marks residing in a specific tic-tac-toe domain. Diagonals through the middle don't count. On each turn, the player in control can place 2 marks, either one in each distinct tic-tac-toe domain, or 1 mark in a tic-tac-toe domain and 1 in the center square. Now, suppose the state of the game is as shown here. Once it is not possible like this to achieve a row utilizing the center square, the only possible solution lie in the domains of the tic-tac-toe games that are joined by the center square. The states of these 2 tic-tac-toe games can be considered independently to find the remaining optimal moves for the duration of the game. Only the game trees for each tic-tac-toe game, modulo the center square, need to be searched to determine the remaining optimal moves. Given the current state, the game can thus be factored into 2 independent subgames at this point. However, from the initial state, this game cannot be factored into independence games because the shared middle square intertwines the two domains as is relevant to the satisfaction of goals in both subgames. While this game is not factorable in general, it is factorable contingent upon entering a state in which no row through the middle is possible for either player. This game is said to be contingently factorable since it reduces to independent simultaneous subgames given that it enters this certain state. It's contingent upon this state. The raw computational benefit acquired from recognizing contingent factors like these is less than that of recognizing initial factors because it requires that the game be in a specific state. However, the relative computational savings are still the same because the number of accessible fringe nodes reduces to the sum of the remaining accessible fringe nodes of the individual games rather than their product. Okay, at this point in time, there are no established techniques for discovering and exploiting cases of conditional independence, although there is some work that is being done right now. However, it seems likely that some of these techniques that we have already discussed can be further adapted, or these new techniques that are being discussed may turn out to have power in finding conditional factors. Okay, game factoring is complicated, as you probably have guessed, but it is really worthwhile. You can significantly decrease the cost of game playing. However, it's not the only source of Propnet-based game analysis that is worthwhile. For example, Propnets can be used to find bottlenecks, that is, games structured in a series where the player must win the first game before playing subsequent games. Propnets can be used to eliminate dead states, that is, states that cannot lead to an acceptable solution and which can therefore be pruned from further consideration. And Propnets can also be used to detect certain kinds of monotonicities, that is, cases where higher goal values on non-terminal states correlate with progress toward terminal states with acceptable goal values. And there's a lot more research to be done in this area.